learning. So federated learning is a framework for learning from distributed client data. And of course, there are many variants of federated learning, but in this talk, we're going to assume that we have a single central server that's trying to learn a single model for a task from the data of multiple clients. And these clients are not directly sharing their data with the central server, but can instead periodically communicate smaller updates, which are to be aggregated by the server to update them quickly. And one of the main goals of federated learning, as outlined in the original paper that introduced it, is reducing the communication costs for clients. So because these could be mobile devices or even IoT devices, communication is considered to be expensive. So we want to reduce how often they need to talk to the central server. And this is going to be the focus of this talk today. So a little bit more precisely, in this work, we're interested in a typical federated learning setting where we have n clients who are communicating with the central server. So in particular, each client has heterogeneous data, which means that their data is coming from different distributions. And I'm going to define heterogeneity precisely in just a minute, but for now, you can just think of it as different clients have different data distributions. And these clients are optimizing some objective function that depends on local data. Okay, so each of the clients has their own local objective. And the central server is trying to optimize the average of all of the client's local objectives. Now, the clients also have to communicate periodically with the server, as we just mentioned, and each time they communicate, we're going to call it a round of communication. So overall, they engage in this process over R total rounds of communication. And so the question that we care about in this work is how can we solve this optimization problem with the fewest communication rounds R to achieve a given accuracy or suboptimality gap while accounting for the heterogeneity of the different clients. And again, I'll make this a little bit more precise. Now, okay, so our goal is to solve this federated learning problem in the fewest rounds. And this is a pretty old and well-studied problem, at least within the context of federated learning. And at a high level, a very common idea for dealing with this challenge is to exploit local computation. So what does that mean? It means that individual clients can take steps on their local objectives in between communicating with the central server. And in fact, they can take multiple steps of optimization on their local objective before communicating. Unfortunately, this doesn't actually work so well on heterogeneous data, at least in theory. So this is a nice figure from the scaffold paper of Karimi Reddy and co-authors. And so here, this is illustrating a concept called client drift. So here the orange boxes, X1 star and X2 star, are showing the local optima for two clients. We have two clients in this example. And this blue box is showing the global optimum, which is X star, which is what the server is trying to learn. And what we're seeing here, this trajectory of blue circles is showing the optimization trajectory for client 2 and client 1 individually as they're optimizing their local objectives. And what we see is that these local trajectories are moving towards the local optima, as you would expect. And the server is taking averages over these local optima. And what ends up happening is that the server's estimate starts drifting away from the global optimum. And this is caused by the heterogeneity of the different clients. So, so exploiting local computation isn't as simple as we might think. If we use it excessively, it's going to cause our global estimates, our global iterates, to drift away from the global optimum, which in turn can increase the communication complexity of our overall optimization problem. So the question that we want to understand is how can we use local computation to theoretically match lower bounds on round complexity? Okay, so what exactly do we mean by heterogeneous in this context? So there's been a few different definitions in the literature. We're going to use one common one. And I'm going to explain this definition in the context of an example. So first, let's assume that each of our client objectives are linear with different slopes, CI. Okay, so client 1 has one linear function, client N has a different one, each of them with different slopes. And our global objective is to optimize the average of all of these local objectives. So because they're all linear, we just end up with a linear function where the slope is the average of all of the local slopes, okay, which I'm calling C bar. Now, our heterogeneity definition, let's parse this expression down here, is taking the maximum over all clients, so I and N, and the supremum over all X in our domain, and it's evaluating the difference between the global gradient and each local gradient. Okay? So it's taking the largest such difference between the global gradient and any local gradient. So in the context of our example, let's compute all of our local gradients. So because these are all linear functions, their gradients, we're thinking of this as a 1D problem. The gradient is just the slope, C1 and Cn. And the global gradient is again going to be the slope of the global objective, which is C bar, the average of all the local gradients. So if we plug this into our expression for heterogeneity, we want to compute the difference between the global gradient, which is the C bar, and the local gradients, which are these CIs. And this supremum basically goes away because this difference is the same for all X. And so in this particular example, our heterogeneity is going to be the maximum over all clients, the difference between the global gradient, C bar, and any local gradient, Cn. All right, so intuitively, this definition of heterogeneity is just capturing how much can the gradients of individual clients differ from the global gradient across the entire domain. Now, I'm going to use a toy example to illustrate two state-of-the-art approaches and show kind of what the problems are when we deal with this kind of heterogeneity. So this toy example is going to have two clients, F1 and F2, and each client has a quadratic local objective. So F1 has a minimum at F1 has a minimum at 1, and F2 has a minimum at -1. And so the global objective,
There's a quick question, I think, in the chat window about whether the previous definition holds also for quadratic functions. I'm guessing you might be getting to that in the example that you're about to cover.
Yeah, so for quadratic functions, of course, this quantity could be unbounded. So in our lower bounds, which I'll get to a little bit later, we end up restricting the domain over which we compute this maximum, compute the supremum, in order to keep this quantity bounded.
Got it. Okay, cool, thanks.
Okay. Okay. So sorry, so the global objective here is f of x, which is this blue curve. And notice that the global optimum here, x star, is -1/3. So it's this point x star here, shown in the black dotted line. However, if we optimize each of these local objectives individually and average their optima, we get 0, which is not correct. So we can't just fully optimize each of the local optima and then average. We have to do something else. Okay. So as I mentioned earlier, one of the common approaches for dealing with heterogeneity is by using local computation, or what we call local methods. So one very popular example of a local method is FedAvg. So here the idea is that in each round of communication, each of the clients is going to start at the current iterate, which we'll call X here. And each of these clients is going to take some number of local steps on their local objectives before communicating. So here we'll take 1, 2, 3, 4 local steps. And then we'll return the resulting xi to the central server. The central server will update, or will aggregate these local iterates, and then we'll resume from scratch. We'll resume this loop. So the problem with FedAvg can be seen from the following. So here in this figure, we have these two regions. We have this yellow region and the gray region. So in the yellow region, which is basically from -∞ to -1 and from 1 to +∞, we can see that the gradients of these objectives agree in sign. So what does that mean? If we look at the sign here, both the gradient of F2 and F1 are both negative. And over here on the right side, the gradients are both positive. However, in this gray region in the middle, the client gradients actually disagree. So one of them has a positive sign and the other has a negative sign. So inside this middle region, there's always at least one client's updates that are dragging the server iterates away from the global optimum because the gradients are pointing in different directions. And in fact, this problem with FedAvg is that when the gradients are disagreeing, you're always having at least one client that's slowing down your approach to the global optimum. This appears also in some sense in the convergence rate. So formally, the fastest known convergence rate for FedAvg is shown here. So here on the left, we have the suboptimality gap. Okay, so x hat is going to be the output after our rounds of communication. X star is our global optimum. Okay, zeta star is our gradient heterogeneity, which is following the definition I mentioned earlier. We're assuming here that the problem is strongly convex. So mu is our strong convexity parameter. R is our total communication rounds. And kappa is our condition number. So we're also assuming smoothness. So kappa is the condition number. So I want to point out two things about this expression. The first one is that it scales with heterogeneity zeta. So in other words, as our problem gets more homogeneous, so zeta gets smaller and smaller, FedAvg is able to take advantage of low heterogeneity to have a lower round complexity. However, the other thing I want to observe about this expression is that it decays only quadratically in R, in our number of rounds, which is fairly slow. So ideally, we would like to get exponential decay for linear convergence. So FedAvg is good in the sense that it can take advantage of low heterogeneity or homogeneity, but it's not great in the sense that it decays slowly with respect to our communication routes. So a different approach, which is very basic, is what we call global methods. So here in every communication round, each client communicates one potentially stochastic gradient update, which gets averaged at the server. Okay, so first we start out with our current iterate x. This gets sent to all the clients. The clients each take one step of gradient descent, which is computed from k stochastic gradients, and return the result to the server for aggregation. Okay, and so this happens multiple times over our rounds. So stochastic gradient descent is an example of such an approach, as are accelerated variants of SGD. Now, if we look at the same figure from before, the problem with SGD is really that it communicates on every update, which means that it's not really taking advantage of client similarity, whereas FedAvg was able to, at least in the yellow regions. And this again can be seen in the convergence rate for SGD, which is shown here. So here again, the left side is suboptimality gap. Delta is our initial suboptimality gap. So the difference between our initial global objective value and the optimal value. R is our communication rounds, and kappa again is our condition number. And here I want to point out two things about this expression. First is that it doesn't depend at all on heterogeneity zeta. So intuitively, this means it cannot possibly take advantage of the low heterogeneity setting because it has to account even for the highest heterogeneity possible. And the second thing I want to observe is that this expression decays exponentially fast in R. So remember, we said we wanted to have this exponential decay in R. So SGD achieves that, but in exchange, it's not able to take advantage of homogeneity. And this can be sped up slightly with acceleration. So basically, we can transform this condition number in the denominator to a square root of kappa, but it still doesn't resolve this issue of not depending on heterogeneity. So if we compare these two, we get that actually, unless the heterogeneity is really small, so less than this expression on the right, SGD actually does better than FedAvg. And notice that this expression on the right can be really tiny because here we have epsilon, which is our desired suboptimality gap, which can be quite small. So this is a little disappointing in the sense that we aren't really getting any benefit from federated learning, at least in terms of, FedAvg, at least in terms of round complexity, theoretical round complexity. Of course, in practice, there are benefits, but theoretically, we don't see it. And so this intuition holds more generally across a variety of settings, including strongly convex, general convex, and non-convex. There have been results showing that local methods work well at low heterogeneity, and global methods work well at high heterogeneity, but we don't really know what to do in between. And existing algorithms are not able to both achieve fast convergence in our rounds R, as well as flexible dependence on heterogeneity. Okay. So that's the problem that we're trying to address in this work. So we propose a federated chaining framework called FedChain that tackles both of these problems. So it has fast convergence across all heterogeneity settings and achieves improved communication complexity in the mu strongly convex setting, general convex setting, and mu PL non-convex setting. And this is the first approach to theoretically improve on both FedAvg and accelerated SGD in different heterogeneity regimes. So what is FedChain? It's a very simple framework. The idea is basically to take your total rounds R. So we assume that we know ahead of time we're going to run our optimization algorithm for our total rounds. And we're going to split those rounds into two segments. In the first segment, we're going to run a local algorithm. You can choose whichever one you like, FedAvg, scaffold, FedProx. And in the second portion of the optimization, we're going to run a global algorithm. Again, here you can choose whichever one you want, SGD, accelerated SGD, Saga, and so forth. And here, a small detail is that in between these two, in between the local and the global algorithm, we're going to take the output of the local algorithm, which I'm calling here x1/2, and we're going to take the better among x1/2 and our initial point x0. And the reason is that our local algorithm could, in theory, bring our iterates further away from the global optimum than the initial point. So here we estimate which is better among the output of the local algorithm and the initialization point. And we feed the better of the two as input to the global algorithm. Okay. And this gives us our final estimate x hat. Okay, so that's FedChain, very simple. And the proof is also dead simple. So I'm going to show you how to prove the convergence rate of FedAvg to ASGD. And I'm going to use this notation of a local algorithm, and then an arrow, and then a global algorithm to denote that the first one is the local algorithm and the second one is the global. So to show the convergence rate for FedAvg to ASGD, we start with a convergence rate of FedAvg. Okay, so remember I showed you this earlier, this expression, and here all the notation is shown on the left-hand side. And for our global algorithm, we're using accelerated SGD, which has this convergence rate, which we also saw earlier. Now, the key observation here is that the convergence rate for accelerated SGD has this dependency out front on the initial suboptimality gap. So all we do is to take the convergence rate for FedAvg and we plug it in, we run it for R/2 rounds and we plug it into this delta. And as a result, we get the convergence rate for FedAvg to ASGD. Here I'm ignoring the effect of that min in the previous slide, but I'll show you how that affects the convergence rate next. So what we can see here is that, okay, so sorry, going back to this bottom expression, we're getting both the exponential decay in R that we wanted and the dependence in zeta, which was one of the key goals. And what we can see is that this actually comes pretty close to a lower bound for strongly convex objectives. So in particular, we can show a lower bound that looks like the following. So we have this exponential decay in R over root kappa. And out front, we have a minimum between delta, the initial suboptimality gap, and this expression that scales with zeta, our heterogeneity. And we can compare this to the upper bound that I just showed you. And we see in particular that the dependency on R is scaling exponentially for both the lower bound and the upper bound. But we do have this factor of R/2 in the upper bound. And this minimum, this leading minimum is coming from taking the better of x1/2 and x0 that I mentioned earlier. Okay. So I want to just briefly give a few details on this lower bound. So roughly the proof structure follows the structure of proof by Woodworth, Patel, and Srebro from their paper Mini Batch versus Local SGD for Heterogeneous Distributed Learning, which in turn is inspired by the classical proofs of Nesterov. But our algorithm class here satisfies two assumptions. The first one is that the optimization algorithm is distributed zero respective. So this means that the algorithm will only have a non-zero value at a current iterate at coordinate I if the algorithm has seen a non-zero entry in a gradient from a previous round, iterate, or client. So in the words of Woodworth and collaborators, this basically just means that your algorithm is not wildly guessing. It only makes updates based on evidence that's seen from previous gradients. And this is assuming that, so here we assume that we start at 0. The second assumption is that the algorithm class is distributed distance conserving. So this means that iterates are not going to move too far away from the global optimum. So what do I mean by this? Let's again look at an example with two clients. So here we have x1 star and x2 star, which are the local optima, and x star is our global optimum. And x init is going to be our initialization point. So here we look at the distance between x init and each of these other 3 optima. And we're going to draw a ball, which is centered on x star, and whose radius is equal to some constant times the sum of these 3 distances, d1, d2, and d init. So when I say that the iterates don't move too far away from the global optimum, we want to ensure that with high probability, our iterates remain within this ball that I'm calling AC. Okay. And finally, another assumption that we make on our function class is that it is what we call zeta C heterogeneous, which means that we're taking the exact same heterogeneity expression from before, but we're only evaluating the soup for x that lie within this ball A sub C. Okay, so this is relevant to the earlier question about dealing with quadratic objectives. So for this, so these are the assumptions that we make for the lower bound, and then basically the structure follows the structure of Woodworth. Okay, so now let's consider, so far I've shown you for a strongly convex setting that FedChain if appropriately instantiated, can achieve convergence rates that are close to lower bounds up to exponentially vanishing terms. Now, one question that we have gotten frequently when we first started sharing this work was, what about sampled clients? So up to now, I've been assuming that all of the clients are participating, which of course in a cross-device federated learning setting is not a realistic assumption. So we extended this analysis to also account for sampling. So here the assumption is that in each round, we're going to sample S out of our N clients uniformly at random. And what happens is if you account for this sampling, we get the same expression from before for FedChain, but we also get this nasty additive term, which is coming from the sampling variance of heterogeneous clients, which is unfortunate because this is kind of drowning out the nice properties that we talked about earlier. So why is this happening? Well, the intuition is that cross-client sampling variance is analogous to sampling variance in finite sum convex optimization. And I'll discuss this in a little more detail in just a second. But this gives you kind of a hint as to what we can do to get rid of it. Ideally, we would like to not have this additive term here. So in the finite sum convex optimization setting, the way that we get rid of sampling variance is through variance reduction. So what we did in FedChain is to add server-side variance reduction in the global algorithm. And what ends up happening is that you can move this additive variance term into the exponential decay term. So here, instead of using accelerated SGD for our global algorithm, we replaced it with an accelerated variance reduction algorithm, SSNM, which is an accelerated version of Saga, which is a variance reduction. Okay, so in a little bit more detail, why is this, what's going on here? It's helpful, I think, to see the parallels with the centralized setting of finite sum convex optimization. And we can see how these two settings parallel one another. So in the centralized setting, we're sampling at each iteration of our optimization, we're sampling S data elements out of N. Whereas in the federated learning setting, in our setting, we're sampling S clients out of N. In the finite sum convex optimization setting, our sampling variance satisfies this relation. Okay, so here sigma squared is our sampling variance. And the thing to notice is that this looks basically identical to our definition of heterogeneity, with the exception that here they're using notation sigma and here we're using this zeta squared. So given these assumptions, we calculate the convergence of accelerated stochastic gradient descent over R rounds or R iterations of optimization and get these expressions that look effectively identical, except in one expression, we have the heterogeneity parameter, which is what we saw on the previous slide. And in the convex optimization setting, the centralized setting, we have the sigma squared. So this gives some intuition why the solutions that have been proposed in the centralized setting could also apply in the federated learning setting. We just need to apply variance reduction carefully so that it has an analogous effect. Okay, so that's how we deal with sampling. More generally, we can analyze FedChain in a number of different settings, including mu strongly convex, general convex, and mu PL, non-convex. And we can see that in some of these settings, the upper bounds that we're achieving are fairly close to the lower bounds. So I want to point out a few things about this table. The first one is that in all three of these settings, the best known algorithm, the best known theoretical convergence rate is an instance of FedChain for different realizations of FedChain. The second observation is that we get close to optimal convergence rates in the mu strongly convex setting, which I mentioned earlier. up to this factor of root s over n, the exponent. And in the mu PL non-convex setting, which is like mu strongly convex, we also get close to lower bounds up to factors of the of kappa. So here we have a root kappa in the lower bound and a kappa in the upper bound. So these don't exactly match, but if we treat kappa as constant, it's okay. In the general convex setting, the upper and lower bounds do not match, but this expression ends up being the tightest convergence rate with sampling to date. And here in this table, just as a note, we've set smoothness beta equal to the initial suboptimality gap, which equal to 1, just to reduce the amount of notation. Okay, so that wraps up kind of the theoretical results that I wanted to talk about for now. And I wanted to show you also some experimental results. How does FedChain actually work in practice? So we evaluated both convex and non-convex experiments. And I'm going to first tell you about our setup for convex objectives. One of the challenges we ran into is how do you control the heterogeneity of clients? So we wanted to be able to see the effect of FedChain over different heterogeneity levels. The way we did this was the following. We started with a homogeneous data set, let's say MNIST. And we call this data set, let's say 30% shuffled, if we do the following procedure. First, we're going to take 30% of samples from each digit. So here each digit is representing a class, a user. So we take 30% of samples from each digit. We're going to shuffle them uniformly. And then we're going to take the resulting column as a client. And so basically the more shuffled the data set is, the more homogeneous it's going to be. So in this way, we can roughly control the heterogeneity of our empirical set. Then we ran an MNIST Logistic Regression, regularized, so it's a strongly convex problem. And this plot is showing you the gradient norm squared as a function of the number of rounds of communication. So here, this blue curve is accelerated SGD, a global method. The orange curve is scaffold, which is a local method. And the green curve is FedChain with scaffold for the local method and SGD for the global method. And this red line is indicating where we transition from scaffold to SGD. And just as a note, the green dots in the scaffold to SGD curve are indicating step size decay, which we also have plots showing step size decay for both of the baselines. They just look a little hairier. So if you're interested, I can show you those at the end of the talk. But what we observe is that for the convex setting, we're seeing pretty substantial gains from running FedChain across various instantiations. So this is just one example that illustrates it pretty clearly. We also observed gains in the non-convex setting, though the gains are a little bit less pronounced. So for the non-convex setting, we evaluated EMNIST, which is a data set of handwritten digits partitioned by author. So here there's 3,400 clients total. And the task was to learn a CNN for digit classification. So this is a standard benchmark from the Federated Learning test suite of Reddy and Charles et al. And in our experiments, what we were seeing is that FedChain seems to outperform baselines. It gives you a bump of a few percentage points compared to baseline approaches. And in particular, what we were seeing was that FedAvg is pretty good for most of the FedAvg or scaffold. Local methods are pretty good for most of the optimization. But then towards the end, if you transition to a global method, it gives you an additional bump of a few percentage points.
Sorry, can I ask one quick question? Can you remind me again how you select when you're making that transition? So
Yes.
this is a fixed number?
So there's two answers. Theoretically, it doesn't matter as long as you have a constant fraction of rounds in the local versus the global portion of the algorithm.
Okay.
In practice, we're treating this as a hyperparameter that you tune.
Got it. Okay. Okay.
And where you switch ends up being a little bit different for the convex versus non-convex setting. So like in the non-convex setting, as I was mentioning, typically we're seeing that you get better results if you switch later.
Okay.
Like 90% of your rounds have already completed.
Okay.
Using a local method. Okay, so Ginger, your question is perfect. It brings me to a question that I just wanted to conclude with, which is how many local rounds do we actually need? So theoretically, when I initially presented FedChain, I presented it as half of our rounds are going to be using a local method, half of them are using a global method, just for simplicity. But what we found is that actually FedChain is pretty robust to different choices of the split between local and global rounds. So for example, what if we use only one local round? So going back to our MNIST Logistic Regression problem, I'm showing you on this slide plots that use a variant of FedChain where we use a single round of our local algorithm, and we run that for many local iterations. And then we use our global algorithm for the rest of the R rounds, R minus 1 rounds. So, okay, so for example, let's look at this, this figure here in the center. So this is 100% shuffled, which means it's approximating a homogeneous setting. The 50% shuffled is a bit more heterogeneous, but both of them display the same trend. So here on the horizontal axis, I'm showing you the number of rounds, and on the vertical axis, we have the gradient norm squared again. And these curves with the little stars are indicating FedChain with a single round of local algorithm, and the remaining rounds are global. And what we're observing is a pretty significant speed up in convergence rates by effectively first optimizing each of the local objectives nearly to completion, and then running global algorithms for the rest of the rounds. So we thought this was pretty interesting and wanted to try to understand why this is happening. So I'm going to wrap up with some preliminary results on trying to maybe explain what's going on, but we don't fully understand this phenomenon yet. So we have some preliminary theoretical justification for why this might be happening, but it requires us to kind of change our definition of heterogeneity. So remember before, our old definition of heterogeneity was looking at the difference between the global gradient and each of the local gradients across all X in our domain. The new definition that we used for this exploration, which I'm going to call delta het, is effectively evaluating which of the clients is guessing the global optimum best. So the definition is the following. It takes the global objective evaluated at the global optimum, which is this term on the right, and subtracts it from each of the local, it takes each of the local optima, xi star, and evaluates the global objective at each of those points. And so our new heterogeneity definition is taking the smallest such gap. So effectively, it's asking which of the clients is guessing the global optimum best, based only on their local objective. So if we go, just to give you an example to make this heterogeneity definition clear, in our previous example, we had two local optima. We had x2 star, which is evaluated at this point, f of x2 star, and x1 star, which is evaluated at this other point, and our global optimum is f of x star. So our new heterogeneity definition is going to take the difference between each of these two local points and the global optimum, and takes the smaller of them. So because f of x2 star is lower, this ends up evaluating to f of x2 star minus f of x star. So this is our heterogeneity definition. Now, given this heterogeneity definition, we tried to analyze a simplified version of FedChain, which we're calling one oracle to ASG. So what do I mean by that? In one oracle ASG, each client first optimizes their local objective to completion and obtains the true xi star, the true local optimum, and returns that local optimum to the server directly. Okay, so this is the main difference between FedChain as I previously introduced it and in this version. And also notice that this is like completely not private. So I'm not worrying about the privacy implications of federated learning for this analysis. We're just trying to understand what's going on from an optimization perspective. Then the client is going to take the xi stars from each of the server is going to take the xi stars from each of the clients. It's going to choose the best one, and it's going to run accelerated SGD to convergence. So basically it initiates accelerated SGD with the best of the local optima that it receives from the clients. Okay, so intuitively, this looks very similar to FedChain. We're just running this initial local algorithm to completion. And it turns out that if you analyze this one oracle to ASG convergence rate, assuming strong convexity and beta smoothness, we get the following convergence rate. Okay, so here delta het, again, is our new heterogeneity definition. R is our communication rounds and kappa is our condition number. So here we get, again, this nice dependency on R, so exponentially decaying R, and we get this dependency on heterogeneity out front, which we wanted. But in addition, we're getting rid of these pesky O tildes that you might have noticed in the earlier convergence rates. So in particular, if we look, okay, I'll come back to that in just a second. But the proof here is effectively identical to what we talked about earlier. So we have our known convergence rate for accelerated stochastic gradient descent from prior work. And all we're doing is taking this initial point, x naught, and we're initializing it with x het star, which is the best of the local optima. And this is exactly the definition of our heterogeneity, our new heterogeneity definition that I mentioned. And so what we're getting here is that this new convergence rate is matching a lower bound, even tighter than the previous results that I mentioned. So in particular, if you recall previously, we had a factor of R/2 in our upper bound that was not present in the lower bound. So we're getting rid of that. And additionally, we're getting rid of the O tildes. So we're getting rid of logarithmic factors that we were ignoring in the previous asymptotic expressions. So here the upper and lower bound are tighter than before. We believe that some version of this result should also hold in the general convex setting, but haven't extended that yet. But I think at this point, we're trying to understand to what extent this approach of fully optimizing your local objectives before launching a global optimization algorithm is useful. So it seems to help in convex settings. In non-convex settings, it's a little bit less clear empirically. So that's basically all I wanted to share with you today. So the takeaways from today's talk are that, first of all, FedChain achieves near optimal convergence rates in strongly convex setting and achieves improved convergence rates across a variety of settings, including strongly convex, general convex, and PL non-convex. And this is the first framework to uniformly match or improve on FedAvg and accelerated stochastic gradient descent across all heterogeneity regions. And I concluded with some basically more questions than answers on, can we get away with a single round of local optimization? So our preliminary results seem to be encouraging, but it's kind of unclear how helpful this approach actually is. So with that, thank you all for your attention, and I'd be happy to take any questions.
Awesome. Thanks, Giulia. That was great. Very super interesting. Also very, very clear talk. Yeah, thank you. If folks have questions, please put them in the chat window or raise your hand, and we can unmute you if you'd like to ask a question directly to Giulia. I have one quick question, maybe while we're waiting. I was curious to know, so it seems like there's obviously an interesting connection between the level of heterogeneity and when you should think about switching from the local approach to the global approach. But I was curious about, because it seems like the results also depended, you mentioned, based on the problem that you were solving. So like for the non-convex objective, the MNIST results, it seemed like that also maybe affected the switching point. So do you think that it's more a function, like, do you think that that's unique to that particular data set in the non-convex setting, or do you think that that's a common trend amongst the like non-convex objectives that you've looked at? I'm curious if it's more a function of like the objective you're solving or the underlying heterogeneity of the data set maybe.
Yeah, that's a great question. I think we're still trying to figure that out. We did evaluate FedChain on multiple non-convex data sets, and we saw similar trends, which is that FedAvg is pretty good for most of the optimization, but then towards the end, if you switch, you do get a bump.
Okay.
I think, yeah, I think this is just a kind of, there's a lot of open questions that we don't fully have a handle on ourselves and are trying to look at. But I think this question of to what extent does it depend on the problem setting versus this heterogeneity parameter, I expect that the problem setting probably has more of an effect.
Yeah.
We're trying to get a sense for how much more.
Yeah. Okay, cool.
I would have maybe like 2 questions. So first of all, thank you for a very nice talk. And so first question is related to your definition of heterogeneity, because like when you compared this like sampling and like heterogeneity with respect to clients, then like your first definition included like max over the client. So the maximum this gap between gradients. But yeah, but in standard like finite sum, and you also showed it, I think, on slide 21, there it's only expectation, so kind of average. And so do you have a particular reason to use actually max, or can you also do the same kind of guarantees with average?
Let's see. That is a good question. I'm not sure off the top of my head. The reason we went with this definition is really mostly to match prior work that has used similar definitions of heterogeneity in the past. So in the sampling case, perhaps you could use expectation over the sampling procedure, I guess is what you mean, right?
Yeah.
Yeah, I think something like that might work out, but I'm not sure off the top of my head, so I don't want to say anything that's incorrect. But yeah, I can think about it a little more and get back to you.
Thank you. And yeah, then the second question is more like practical. So your algorithm depends on R, so you have to know the number of communication rounds. Is there actually any workaround to still run your FedChain algorithm if you don't know how many rounds you're going to run?
We have not tried that. Yeah, so as far as I know, there's not been any work on that question. Though I suppose like one thing that we did notice, maybe if I go back, one thing that we did notice is that after some point of running your local algorithm, it does kind of plateau. And at that point, maybe you could make a decision without knowing the total number of R's that, okay, I'm not getting enough benefit anymore. And now I should switch to a global algorithm. So I feel like one could come up with some heuristics and probably see some benefit even without knowing.
But I guess here problem could be that you actually like to computation of like the full gradient norm, it kind of involves all the clients, and that's something that you're not going to have in practice.
Yeah, that's true.
So you kind of can't estimate that.
And yeah, that's true. You would have to estimate. You would have to have a best and noisy estimate of this. Yeah. So even even actually in this point in FedChain where we're taking the better of the two iterates. Here we compute this through a noisy estimate of the global objective by sampling S out of n clients.
So just one more question. Can you go back to the previous graph that you just showed, the scaffold?
Yes.
Yeah. So here, could you please give more details why scaffold is not the same with your FedChain until the transition?
Yeah, good question. This is because in the scaffold baseline, in the FedChain baseline, we were doing step-size decay, and in the scaffold curve, we are not. So I can actually show you a plot where we're doing step-size decay on both. It's a little hairier. Let's see. So, okay, so here the M hyphen are the multi-stage step-size decays. So let's see. So here M scaffold is the gray diamonds, which is kind of hidden behind the blue ones. But you can see this gray curve kind of flattens out in the end, whereas the M scaffold to SGD is kind of separates once we transition from the local to the global algorithm.
And what's here the rule to decrease step size?
Sorry. Oh, the rule that we were using was every power of 2 rounds, we have the step size.
Thank you.
Sure. Any other questions?
I have maybe one last quick question, but other folks definitely jump in if there's anything else you want to ask before we head out today. I was curious about, so the last approach is quite interesting. Is the way to understand that you basically run like a one-shot averaging approach where you completely solve all of the local objectives, average them together, and then that's your initial starting point for running a global method? Is that the way that works? Okay.
Yep.
What I was curious about, so the results that you have now, does that assumes full device participation, I guess, amongst all of the, like you get the objective from all of the devices, is that right?
Yeah,
okay.
That's right. Mm-hmm.
Okay. Yeah, I was curious about how, that might be something easy to extend, actually. I don't know if that's that interesting, but how having partial participation in that component would change things. It seems like there has been some prior work, I guess, right, on one-shot averaging, but I think it's mostly been in the convex setting, and I don't know how it's taken into account heterogeneity. Yeah, I don't know.
Yeah. I'm not too sure. I don't think that I haven't seen anything that took into account heterogeneity, but it might exist.
Yeah, I think I just think that might be like on its own also quite an interesting setting to consider. It's just like, how good is the estimate you get from just this one-shot averaging technique? But then also the refinement, I think, is pretty interesting to look at. Cool, and that also has the nice benefit of exactly when the transition happens, I guess.
Yes, that is true.
Yeah,
avoids these questions on when to switch.
Yeah, super interesting. Okay, cool. Any other questions from folks? All right. If not, yeah, thanks again, Giulia. We can thank the speaker again. And I think we'll head out for today, given that I think we're at the hour now. So we'll have the recording online for folks, and hope to see you again another week soon. All right, see you, everyone.